In this video, I'll introduce SwitchApp, Arista's low-latency switching application for our 7130 series of Layer 1 products. SwitchApp offers a full set of Layer 2 features, with latency as low as 95 nanoseconds port-to-port. Future releases will include Layer 3 protocols, including BGP, PIM, and NAT. SwitchApp is an FPGA application for the 7130LB platform. So to get started, let's first review its hardware architecture. Internally, a low-latency crosspoint chip connects all front panel ports to an FPGA. Unlike a traditional network switch, any of the front panel ports can be connected to any FPGA transceiver. We handle this in the configuration by naming front panel ports Ethernet 1 through 48 and the application ports 1/1 through 60. You can configure the crosspoint to connect any of these interfaces to any other with about 5 nanoseconds of latency. When SwitchApp is installed, we get a new set of switch interfaces that are internally mapped to application ports. All of the switch config goes under these interfaces, so when SwitchApp is installed, you can consider the application ports in implementation detail. In EOS, 7130 FPGA applications are managed as extensions. If you want to move from a different app to SwitchApp, or upgrade SwitchApp versions, you simply uninstall the existing extension and load a new extension file. Let's install SwitchApp and start configuring it. First, we'll copy the Swix extension file over to local extensions, and then we'll install it. Here I'm copying from Flash, but I could copy from an HTTP server, FTP server, wherever is convenient. We can check its status with Show Extension, and you can see I have it installed and active now. Then we'll make it persistent on boot and enable it. When I enable it in the configuration, the system will program the FPGA. After a few moments, we can check the status with Show FPGA Switch. Here we see that the FPGA is programmed and ready to go. We also see that we have a new set of switch interfaces ready for configuration. By default, each front panel port is mapped one-to-one to a switch port. We can check the port mapping with Show L1 Path. Here we see that switch 1.1 is tied to Ethernet 1, switch 1.2 to Ethernet 2, and so on. But this is still a Layer 1 box, so we can change these mappings. The L1 source command ties arbitrary ports together. Let's say I want the output of switch 1.1 to be replicated to front panel port Ethernet 4, like this. This effectively creates an outbound tap. Well, this is easy to accomplish. I go to the front panel interface, Ethernet 4, and I set its source to be switch 1.1. I can also replicate traffic coming into the switch. If an exchange's market data feed is coming in on Ethernet 1, it would normally be fed through the crosspoint to switch 1.1. But I can instead replicate that to other ports before it even hits the switch, distributing that data in only about 5 nanoseconds. Let's say I want to copy it to Ethernet 3 and 5. Well, I can go to those interfaces, set the source interface to be Ethernet 1, the other front panel port, and I'm done. And of course I can go back to the L1 path command to verify that I have all the connectivity stitched together properly. The L1 source command connects a port in one direction. If you want a bidirectional mapping, you'll need to use a source command twice, once on each side. Since this is such a common operation, we have a shortcut for it, L1 connect. Here L1 connect Ethernet 1, Ethernet 2 connects the TX and the RX lanes of Ethernet 1 and 2 together. But under the hood, we can see this just uses multiple L1 source commands. Now, as you're stitching together the Layer 1 infrastructure, you might lose track of how things are connected. We have another way to look at this in addition to the L1 path command, and that's Show L1 Matrix. This gives you a graphical view of how ports are connected together. Okay, let's go back to the default config, which maps front panel ports directly to individual switch ports, and I'll show you some of SwitchApp's features. You'll see it feels like a typical switch. We'll start with the show interface on switch 1.1. You'll see we have the counters and status that you'd expect. We support spanning tree. This is currently configured for MSTP, but we do support rapid as well. And all of the interface options are also here. We support LLDP, although as you can see I don't have a whole lot connected in this lab, And we have ARP tables and a MAC address table as you'd expect. So now let's jump into some configuration. We'll set up a couple VLANs, VLAN 5 and 10, and we'll set switch port 1.1 to a trunk. And we'll make it have a native VLAN of 5, just for fun. Next, we'll set up switch port 1.2 to have an access VLAN of 5, and port 1.3 to have an access port of 10, VLAN 10. So, no surprises here. We can take a look at the MAC address table and see that things have moved around a bit, just as we'd expect. Next, let's set up a port channel. We'll go to interfaces 147 through 48, set up a channel group, you can verify that the port channel is now up, and we have a couple status commands as well. And finally, we can set it as a trunk. SwitchApp also supports Layer 2 Multicast. We can set up IGMP snooping by defining a courier. We'll set one up globally. First, we'll enable it, and then we'll set the address. And then verify its status. If we want to statically map a group to a given port, we can use an IGMP snooping member command. Here we're assigning 239.193.1.1 to interface 1/2. And we can confirm the configuration with show IP IGMP snooping groups. SwitchApp supports a few different profiles to optimize latency. Currently we have two profiles. One that optimizes for the lowest possible latency by reducing cross-sectional bandwidth, and another that provides a full 480 gigs of bandwidth. You can see what the current profile is with Show FPGA Switch. You can see here we have the Layer 2 full profile. The Layer 2 low latency profile reduces the cross-sectional bandwidth to achieve about 95 nanoseconds port to port. You can easily change the profile with the profile command under the switch configuration. Some profiles will support multiple speeds. The Layer 2 full profile supports both 1 gig and 10 gig, and you can check this with Show Interface Hardware. The command line isn't the only way to manage SwitchApp. Since we're running EOS, we also have access to eAPI. eAPI is a JSON RPC interface. Anything you can do at the command line, you can also do through eAPI. Responses are JSON with individual fields broken out, so you don't have to deal with parsing or screen scraping. Here I've enabled the eAPI Explorer. eAPI Explorer is a playground for eAPI on a switch. You can try out different commands and see the responses. It also includes an overview of configuring eAPI, including TLS support, and documentation for all the different command responses. Let's try out some commands. First, I'll enable autocomplete so I can type partial commands. And let's go with Show Interface Ethernet 1. On the left, you can see the request that was sent. And on the right, you can see the response. All of the fields that you would normally see at the CLI, you can see here in a structured format. You can also change the configuration with eAPI. Let's change the description of interface Ethernet 1 to change from eAPI. And I can double check this at the command line. And you can see it has been changed. eAPI Explorer also includes a script editor that has some sample scripts in JavaScript. You can see here, this one prints the system MAC address. Let's say we want to update this to show the MAC address table. Well, first we need to see the shape of the response so we can pull the fields that we're interested in. I'll send the request for Show MAC address table and check out the response. You'll see the result includes a unicast table key with an array called table entries. I can easily print out the table by just iterating over this array. I'll use for each and the MAC address field. and run my script, and you can see I've got the full MAC address table. You can use this approach to access any field with the API. And while these examples are in JavaScript, any programming language that can send and receive JSON can use eAPI. If you need more advanced integration, such as directly modifying the switch's state, you can use EOS SDK with Python or C++. Well, this was just a brief overview of SwitchApp and the software ecosystem around it. There's much more to come. We'll be adding a full set of ultra-low latency Layer 3 features, including BGP, PIM, and NAT, in future releases. Stay tuned. Thank you.